Hello everyone and welcome to the Oxford Martin School. My name is Charles Godfrey, I'm the director. Looking around the audience, I recognise that there are people in the audience who were here on the 23rd of March when Steve Cowley, who used to be the interim director here, talked about fusion and the work that was going on in Princeton. And you'll recall that he went off on a tangent to say about some of the really exciting things that were happening just up the road from here. And he said in his talks, you really must get Ian Chapman down to give a talk. And so we have done that. And Ian Chapman, who is the director of the Harwell program, is going to be talking this afternoon on the pathway to delivering fusion power. Now, I'm going to get you started, but the person who's going to give the vote of thanks and organise the questions is David Gann, Professor David Gann. Now, David is our Pro VC for Development and External Relations, but also has another life as chair of the UK Atomic Energy Authority. So he's got special expertise in that. So with no more ado, Ian, please give your talk.
Thank you very much. That's yours? Okay. Yeah, it's a real pleasure to be here. I refuse to believe that Steve went off on a tangent. He never does that. And I now feel very underdressed because I see Tim in the audience with a tie on, which I almost never see. So, yes. Anyway, look, the fact that you have given up an hour of your time to listen to a talk about fusion means you probably know that we have a serious problem with climate change. I realise I don't need to do a hard sell about why climate change is important, but I'm going to show three graphics which I think are very illustrative. This one just should scare you. World record temperatures all over the place last year or this summer, and it's only going one way. This little movie that was released by NASA earlier this year shows the global average temperature, so averaged across all bits of the globe by month for the last 140 years. And for the first 50 seconds of this movie, nothing happens. It's very boring. So the global temperature just doesn't change, and it continues not to change for a long time. But all the time, we're layering on carbon over the top of this and layering on insulation on top of the world. Still nothing really happening. Temperature's not really changing from the 1900 level, which is against which this is baselined. Still in the 70s, nothing really happening. People getting more climate conscious at this stage and modelling about the implications of climate change are definitely with us by the 70s and 80s, but not a lot happening. Even by the 2000s, it's not very dramatic. But then in the last 20 years, things are going only one way. I think when you look at that cut like this, it's really pretty scary. Where you see nothing's happening while you're putting insulation over for 100 years. Nothing really happens, and then it all begins to go in the wrong direction. And the inertia in the system, which is very clearly illustrated by this, shows you how hard it is to turn it back the other way. So this is an oil tanker heading in the wrong direction with a lot of inertia. I get quite frustrated when talking to policymakers about how glib people are about net zero. So there's this phrase now, all around Whitehall, net zero by 2050. It's like it's a done thing. It's anything but a done thing. And I think this illustrates it. So this shows you the root source of our energy and consumption over the last 120 years. You can see a couple of scary things about this. I mean, it's all going up. You all know that. All of it is going up. All the carbon sources are going up. If you add up the red, the orange, and the black, so the fossil fuels, roughly speaking, it's 11 gigatons of oil, roughly, okay? So the concept of global net zero by 2050 means that, for sure, irrespective of increase in demand, we've got to displace that. So we've got to displace 11 gigatons of oil by 2050. So let's try and actually put that in context. So 2050 is, roughly speaking, 11,000 days away from now, roughly. And we're talking about 11,000 megatons of oil. So you've got to get rid of 11,000 megatons of oil in 11,000 days, roughly. So it doesn't take a genius to think, okay, we can do a megaton of oil a day, right? So what's a megaton of oil? Well, a megaton of oil is like Sizewell, the biggest nuclear power station we have in the country, or Hornsea, the biggest offshore wind farm in the world. You've got to do one of them every single day for 30 years, just to displace what we burn today, let alone increase in demand. And I think patently we won't do that, right? We just patently won't achieve that. So being glib about net zero by 2050 is I mean, horrific, really. In big handfuls, either of these projects, right? Either of these projects cost about 10 billion. So you've got to spend 10 billion per day to displace just what we burn today, let alone increase. That's roughly 4% of global GDP. So that's what we should be spending. We're spending kind of 2 orders of magnitude less than that. And there's no real imperative to address this problem. So this is all horrific and very miserable way to start a talk. So what are we going to do about it, right? And I often say to government that you could do a lot worse than take science policy advice from Stephen Hawking. This was what Stephen Hawking was asked and published on the last page of his last ever book. He was asked, what do you want to see humanity do? Anything. What do you want to see humanity do? This is easy. It's not easy, unfortunately, but this is easy. I'd like to see the development of fusion. And fusion offers loads of potential. I think you all know this, otherwise you wouldn't be in this room. It doesn't produce carbon. It's inherently safe. You don't get a runaway or a chain reaction. It's reliable in that you don't wait for the wind to blow or the sun to shine or seasonal variation. It could be running all the time if we can make it work. It's sustainable in the sense that we get our fuel from seawater and lithium, and we have lots of both. And it's hugely energy dense. And I really care about the last one because in this country, right, when we're talking about net zero, the government generally thinks quite parochially and thinks about UK domestic energy policy. And in this country, we should do offshore wind, and we should do offshore wind at scale. We're a small, windy island with a shallow seabed. We're just about the best place in the world for doing offshore wind. But unfortunately, that doesn't apply to most other countries. And we, unfortunately, are less than 1% of the global energy market. So we can go net zero, and who cares, right? Some brilliant people in this place were working on vaccines, and they didn't have the attitude of solving the vaccine problem for the UK. They had the attitude of solving it globally. And if you don't have the attitude of solving climate change globally, you don't solve it. So it's pointless thinking parochially. You have to think big. And that means you need an energy-dense process, which works in all jurisdictions. And that's one of the reasons that I think fusion is so important. But it's really hard, right? And you all know that. To make fusion happen, we have to take the fuel to a temperature which is about 10 times hotter than the center of the sun, about 100 million degrees. And to do that, we obviously cannot let the fuel touch the walls of the device. So we use very large magnets to keep the fuel away from the walls to make sure it doesn't melt parts of the device. And then you suspend that fuel using very large magnetic field. Right, so that's the basics. So what am I going to talk about tonight? You probably all knew all of that. I'm going to tell you a little bit about policy, so what the government's policy on fusion is, and not just this government, but governments around the world. I will spend most of the time talking about technical challenges and things that we are doing in the UK to start addressing some of those technical challenges. And then I'll finish with some ideas about what's required to actually deliver and actually take this to commercial reality. So first of all, on policy, I'm going to tell you about 4 different global government policies, starting with the EU. And I would say the EU were the forerunners, really, in thinking about how to actually commercialize fusion, how to actually get to power plants. And they wrote down, about 10 years ago now, a pretty comprehensive roadmap to get to power plants. I describe that as a sort of evidence-driven roadmap. So they're first of all thinking about, well, you know, how are we going to sustain fuels at that temperature? How are we going to protect the walls from that sort of heat? How are we going to do with the neutrons that are produced? And I'll talk more about all of those things later. And so before moving to the next step of the roadmap, there had to be evidence. There has to be a technical solution, not just conceived, but demonstrated. And then you move to the next step. So it's a sort of evidence-driven, sequential roadmap. And that means if you take that philosophy, you end up with the first demonstration of a power plant in the 50s and, you know, commercial power decades after that, because rollout time takes decades in all bits of the energy industry. So that's a sort of evidence-driven approach. And then in the last few years, we're beginning to see governments adopt a more aggressive schedule-driven approach, where they're aiming to try to bring that forward and maybe parallelize up some of those activities or take more risk and say, well, we're not going to wait till we've got evidence, we're just going to move forward at risk of the asset not working. And so the UK government published last year a fusion strategy. It's the first time they've ever had such a document. And it has two goals. The first is that we build a prototype to demonstrate that you can produce fusion power and actually put it onto the grid. even if it's not cost competitive, it doesn't run much of the time, just put it on the grid and show that it works. And secondly, to establish an industrial capability to actually export that. Now, as I was talking about before, you have to have a solution which goes globally. Well, to do that, you need an industry that can support that. So the UK wants to be at the forefront of this. But the UK is not the only one that wants to be at the forefront of this. So you will have heard from Steve about the US fusion strategy. And the US government are, I would say, waking up to the opportunities around fusion. The White House in March had a summit aiming for a decadal fusion vision. And some of the things they said was, well, the UK is getting its house in order, the Chinese are getting their house in order, and so the US should respond. The US currently spends about $720 million a year on fusion. We expect that budget to go up substantially in the next appropriations period. And as a sign of that, just 10 days ago, they launched a public-private partnerships program to start building a pilot plant. And so they will take forward a few concepts co-funded by private money and public money to start designing power plants. And lastly, I thought I'd mention China. I will talk later about ITER, which is this very large consortium program to build a next step experiment which shows that you get a thermal gain, so more fusion power out than put in. All of those countries I just talked about are members of ITER, and the Chinese are members of ITER, and they have very openly said they've gone into ITER, they put in 9% stake for access to 100% of the IP, and they will build machines which look roughly like ITER, and they'll build them on volume, and try to drive down price by doing volume. It's sort of standard Chinese approach. In parallel to that, they are building a number of technology demonstration test facilities, which is in this science park on the left-hand side. That is now almost built. It was a figure from 3 years ago, and it's now very close to reality. They are working on a power plant design which has this very large ITER-like design, which is this machine here, and they've identified a site for that, and they're getting going with it. And they're now talking about also building an intermediate device, which comes before this, to gear up their own operational capability, maybe by 2030, comparable to the jet facility that I'll talk about in a minute. So that's what's going on in the world, to give you some context, and the race is definitely hotting up. So let me talk about some of the technical challenges that any of those policies all have to tackle, these technical challenges. Today, we don't have a working fusion power plant, and that's where we want to get to. Something that looks roughly like this, it's big infrastructure, it's like power plant scale, would replace the gas plant or the coal plant that you see as you drive along the motorways. And that means tackling 5 big technical challenges, in my view, 5 things that we have to overcome. The first, and sort of the one that people know about, is that the fuel has to be hotter than the center of the sun to make it fuse. This is real footage from the inside of JET, which is still the largest and best device in the world today. And only at those temperatures, when you take the fuel to 100 million degrees plus, do you get a decent reaction rate between a deuteron here, this is a deuteron whizzing around the inside of the machine, so heavy hydrogen. At that energy, will react, will have a decent cross-section with a triton, very heavy hydrogen. They fuse together and they produce helium, inert gas, not worried about that, and neutrons. And most of the energy goes with the neutrons, and the neutrons allow you to actually produce electricity. So that's how you produce electricity, capture those very energetic neutrons. Now, they're very energetic, which is great for electricity yield, but this is the most intense neutron source on the planet. And as those neutrons stream through whatever you've built the machine from, be it steel or tungsten or whatever, it will cause displacements in that lattice. And as you change the structure of the lattice that materials are made from, it changes its brittleness and its strength and its creep, essentially how long it lasts, which affects the cost of the consumer. The third challenge is that as well as an incredibly intense neutron source, you have to deal with huge heat and heat gradients particularly. So the bit in the middle is 100 million degrees. The wall, which is sitting 2 meters away, has to be less than about 2,000 degrees or it melts. And immediately behind that, you have magnets which are cryogenically cooled to almost absolute zero. So you go from 10 times hotter than the sun to almost absolute zero in the space of 2.5 meters. It's quite a big thermal gradient to deal with. The fourth challenge is where you get your fuel from. So we use deuterium, which we just take from seawater. There's plenty of seawater, so plenty full supply of deuterium. And then tritium, which is radioactive but short half-life. It's about 12 years half-life, so you have to make it. It doesn't exist naturally anymore, we have to breed it. This is meant to represent a blanket of lithium that we put around the outside of the machine. The neutrons stream through that lithium and some will produce tritium. Then you take that that material out into a processing plant at the back end, extract the tritium from it, freeze the tritium into little pellets, and then fire those pellets into the machine. So this is putting wood on the fire. Keep throwing wood on the fire, it keeps burning, keeps the reaction going. Stop throwing wood on the fire, it stops. So unlike a fission machine, where the rods go in and you've got years' worth of fuel, in a fusion device, you've got a few seconds, 10 seconds maybe, of fuel. So if you want it to stop, it stops quickly. And then the fifth challenge is that you can solve all of the first four, but if you only run for half the year, the cost to the consumer will be chronic, and so nobody will buy that electricity. So you need high availability, high uptime. Because we have tritium, which is radioactive, and we produce neutrons, which irradiates things, we can't really send people into that environment. So we need big robots like the one you just saw on the screen to go in, replace the tiles, get out, and get operational again. So for the next half an hour or so, I'm going to talk about those technical challenges and say a little bit about what's going on here in the UK to address some of them. So to start with, the notion of having to sustain a fuel which is hotter than the sun, we do in this device. So this is JET. It's the largest device in the world. Here you see a person. So a person in coveralls, to give you some sense of scale. It's a proper industrial plant. It's unique. It's the only machine that can handle tritium inside a tokamak, the only machine with a robotic maintenance system, the only machine with the same mixture of metals that you might use in the armor of a power plant, the only machine of its scale. It's just unique. And this year, we set a new world record for fusion energy released. The last time that we operated with this mixture of fuels, deuterium and tritium, was in 1997, so 25 years ago. And we produced the red curve there for fusion power produced when we were trying to sustain it and keep it going. This year, we produced either the blue or, in an optimized case, the pink case. So a significant increase in the fusion energy released. Now, in and of itself, I mean, actually, that's not very impressive. It only lasts for 5 seconds. It was only 11 megawatts. And actually, it took us a lot more energy and electricity to produce that small amount out. So some context. JET is only an experiment. It was built in the 70s and 80s. It has copper magnets, which means it consumes a huge amount of electricity to produce the magnetic cage. So if you look at the total power going into those magnets, it's like a gigawatt. And then the heating power going into the plasma is maybe 30 megawatts, and we produce 11, right? So it's a small amount of fusion out compared to the electricity going in. ITER, the next step device that I'll show you in a minute, the aim is that the power out is roughly the same as the power needed to run the device. But it's not going to produce electricity, so it's a sort of net zero. In a power plant, the power produced out, so the electricity produced out, is much bigger than the power to operate all the elements of the plant and the ancillaries. So that's what we're aiming for. That's where we are today. But the fact that those curves pretty much overlie our predictions gives us high confidence that we now understand the dynamics of the fuel and understand how to control a hot fuel on the inside of these machines. And that means that we are now proceeding with this project. So this project is a multi-country project. There's 35 different countries involved in it. It will be the biggest scientific collaboration ever undertaken by humanity, actually. It's about 80% built now. We were building that at risk. So we had not demonstrated the things that we've just shown in JET before we started building it. We were hoping that we would demonstrate them in JET, and we now have. And that gives us confidence that we'll reach the goals of this machine. So the aim of ITER is that you put 50 megawatts thermal power in to heat the fuel, get it hotter than the sun, and then it will produce 500 megawatts of thermal power out, so showing that you can do fusion on a commercial scale, roughly commercial scale. We're hoping that this machine starts operation in 2026. It's an unholy alliance, really. If you're good with flags, you know all these partners, and they're not exactly natural bedfellows working together. But the project is still working together, all partners still engaged. It had a lot, as you might imagine, of teething problems, sort of very complicated geopolitics. It's really not the way you would run a big engineering project if you set out to do things in the most efficient way, but it required all of those partners to come together to make it happen. To give you some sense of scale, this bit in the middle is about 80 meters across, it's about 120 meters long, it's about 80 meters tall. So this is one of my bad jokes. I say it's like Wembley. It's about the same scale as Wembley, about the same amount of steel as Wembley, and like Wembley, it's about twice over budget and twice behind schedule. But it is much more complicated than a football stadium. I'll show you a quick fly-through. If this works. Oh, no, movie not going to work. Oh no, I can't show you a quick fly through. What a shame. Oh well, if you go on the ITER.org, you'll be able to get a fly through of the machine, and it's really very impressive. I'm really sorry that didn't work. Anyway, don't know why. However, ITER is massive. It's really, really enormous. To give you because I can't show you the movie, I'll give you two stats about it. The vacuum vessel inside which the fuel is held is about 60 meters circumference, and like segments of an orange, you build the wedges and segment them together. That 60 meter circumference has to be welded to 2.5 millimeter precision, which is just incredible, and it was done to less than 2 millimeters precision, the first welds of those two segments being joined together. And then the magnet that goes down the middle, which produces the magnetic field to trap the fuel, that magnet that goes down the middle produces a magnetic impulse which is roughly equivalent to the weight of an aircraft carrier at strongest force. So just get your head around that, put a magnet over an aircraft carrier, lift it out of the ocean. It's bonkers, right? Absolutely crazy, but yet that now exists. So that magnet has been wound, and most of the segments are now on site. So it's the whole establishment of a supply chain that didn't exist, capabilities which didn't exist, mind-blowing engineering. But it's really big, and it's really expensive, and the way it's being run as this geopolitical consortium makes it pretty slow. So can we do better? Well, really, really excitingly, earlier this year, a spin-out company from MIT, a company called Commonwealth Fusion Systems, produced a new magnet. This is a pretty big magnet, so it's 3 meters across, 10-ton magnet, which showed a new world record for magnetic field on that scale. It's 21 Tesla. The magnets in ITER are about 12 Tesla, so it's almost doubling the magnetic field. And magnetic field's a good thing for fusion. More magnetic field means more fusion power produced. So this is a really exciting breakthrough and offers a pathway to more compact power plants. There are other technical challenges that are introduced by this, for sure, but it is an exciting development. The second thing I'll talk about is how the neutrons which come out the inside of the, when the fusion reaction happens, neutrons come out and stream through the walls, how they might damage the materials. So each one of those neutrons can displace an atom in the lattice, and what really matters is when you end up with cascades of displacements, and those cascades can cause lots of displacements from their natural lattice sites, which then might last for a long time, cause voids in the material, change the plasticity and the structure, and ultimately cause dislocations in the material, which fundamentally affects both its mechanical and thermal properties. The other thing which the neutrons do is cause transmutations in the material. So what you might put in as pure tungsten to start with undergoes lots of transmutations, and you end up with what was pure tungsten having a big chunk of rhenium in it and osmium in it, and that again affects the properties of the material, its longevity, and that affects the lifetime, which affects the consumer's price. So we really need to understand this. We don't yet understand it fully, and we certainly don't have materials which are going to last within this environment for the lifetime of a power plant. So we built this facility a few years ago to try to understand the properties of those materials. So we might put a material into a test reactor, neutrons come through it, irradiate that sample. Typically the sample comes in about finger-sized. It gets loaded robotically into that series of hot cells, chopped up into sort of fingernail-sized, and then moved into one of now 20 different research rooms where it's unloaded robotically into an instrument which then analyzes the properties of that material at a micromechanical scale. And the user is all remote from that, so it's all done robotically. So that allows us to really understand, at a very small scale, the properties of that material. But you do need to scale that and think about, well, what does it look like on a centimetre scale, and then how does it behave on a metre scale? And so those are the next challenges that we face. As well as the neutron source, we talked about incredible heat gradients. So in the middle, you have a fuel, which is, as I said, hundreds of millions of degrees, a wall, which has to be a few thousand degrees. And you see, because of the nature of the design of the device, most of the heat, this bit you want to keep it hot, but like, I don't know, air over an aeroplane wing, water down a pipe, they suffer turbulence. You're putting a huge amount of energy into something which is about 100 times thinner than air, and so lo and behold, there's some turbulent processes going on. And so some of the hot material will get out to the edge. And we don't just let that hot material go out and hit the wall. We use magnets to sweep it down to a sacrificial surface down at the bottom. So you can see that in the infrared image here of jet, where all of the heat is ending up down at the bottom. And those sacrificial surfaces you'd have to replace every few years in a power plant. Now, ITER is designed like that, but if you want to think about making a smaller power plant, if you want to try and drive down the scale and drive down the cost, that means that, you know, the boundary condition is still the same. You still need the fuel to be the same temperature, it doesn't fuse. So the bit in the middle must be 100 million degrees. If you put that heat source into a smaller volume, into a smaller box, then the chances of damaging the walls of the power plant are obviously a lot higher. So you need an even better way of extracting the heat, exhausting the heat without damaging the walls of the device. So we've been working on this for some time. We built this device over the last 10 years or so, a machine called Mast Upgrade, which last year won the Royal Academy of Engineering Major Project Award, of which we're very proud. And the aim of that device is to demonstrate a novel way of extracting heat from compact, small machines. So I'll try and describe how this works. So the bit in the middle, as I said, needs to be really hot. Some of the material gets out to the edge, and we sweep it down to a sacrificial surface at the bottom. Now, if you built a compact machine like that, that sacrificial surface might only last weeks or months. It's definitely not got the right lifetime. So instead of hitting a surface here, in our new device, we've swept the heat out about another 50 centimeters along in real estate before it hits the wall out here. Now, whilst that doesn't take up a lot of space, the particles are going around and around and around, still in 3 dimensions as topologically a torus, so they go around and around and around. And so that 50 centimeters of space, of exhaust pipe down at the bottom here, is actually buying you 20 meters of pathway, so to the wall and back again. And the whole time the particles move along that pathway, they radiate energy and cool down. You can also fill this chamber, which is physically pretty detached from the hot bit in the middle. You can fill this chamber with gas, cool gas, so that as the hot particles come in, they'll undergo all sorts of radiative losses in that gas cloud and spread the heat over a much bigger area. So our aim was that by doing this, we would drop the heat, which actually gets to the wall, so the heat flux impinging on the wall, by more than 10 times. This is what we were aiming for. So the conventional line here is how ITER's designed, how most conventional power plants are designed. And the blue line is the approach that we're taking in our new device. So we're aiming to reduce the heat by 10 times. And if you can do that, it opens a pathway to a much smaller device because you have a clever exhaust system. If you don't have this, if it doesn't work, you definitely can't build a small device because it would just melt the walls. So that was the challenge we set ourselves. We published that 10 years ago. Scientists in the room know that making predictions like that 10 years in advance is a dangerous thing to do, because you stake your reputation on it. So we then built the machine to test this notion, and these are the results that we got last year. And if you want to see experiment match modeling, you could do much worse than that, frankly. And this shows me 2 things. It shows me that the system works, that it really does reduce the heat which is getting to the wall. And secondly, that we have some capability of saying what future devices might look like. So this is hugely exciting. It really offers us a pathway to a more compact plant. If you combine those 2 aspects of dealing with high heat and dealing with the neutron load, that takes us on to then thinking about, well, how are components, big-scale components, going to last in that very challenging environment? So to test that, we're building another device, actually in Yorkshire. And this is a test of a component. This component in the middle, which is the sample under test, is about my size. It's about 2 meters by about 1 meter, nearly 1 meter wide, sadly. And that component then gets put under a very high heat flux, so really, really strong heat flux, in a 4 Tesla magnetic field in a vacuum. So the conditions that you find on the inside of a fusion device. It doesn't yet have a neutron load, it's not irradiated, but it does test that combined load of strong magnetic field in a vacuum under high heat flux. We will then put also a pulsed magnetic field, which simulates any sort of off-normal events, and a pulsed laser, which again allows you to put off-normal spot heating onto that device. And there's nothing else like this, genuinely nothing else like this anywhere in the world for testing components on scale. So you can test all the brazes and the welds and the joints, the things which typically usually fail, not just the micromechanical stuff. The 4th challenge we talked about was where we get our fuel. So deuterium we just take from seawater. Tritium, it's radioactive, half-life, half-life of about 12 years. Where are we going to get it from? So the idea is that fusion happens in the middle. You take deuterium and tritium in, fuses, produces helium neutrons. The neutrons then stream through a blanket made of lithium, typically lots of lithium-6, also some lithium-7, and that produces tritium and helium. The tritium you then need to extract and put back into the middle. So you need to produce enough tritium that you can keep burning the fuel. If you don't produce enough tritium to feed back in, then you don't last very long because you have a startup charge which fuses, burns, and stops. So you need to keep putting wood on the fire. You need to keep putting fuel in. So it's really important that we can demonstrate this and that we understand how it works. We've just completed the build of this building, which will be soon the largest tritium research facility in the world. And on the inside of it, this is a block diagram, which will go into more fidelity, is a full tritium plant. So it goes from storing the tritium, radioactive hydrogen, how we store it, how we extract it from storage, how we freeze it, inject it into vacuum, mix it with other gases, then take it out afterwards, separate the gases, separate the isotopes of hydrogen, deuterium, tritium, and then put the tritium back into the storage loop and account for the whole thing around that loop. Again, there's nowhere else that does that full loop anywhere today. So that facility is now well under construction. These components are well under procurement. They should be operational in about 2 years' time. And then the last challenge that we talked about was the maintenance and how you maintain the device under those pretty exacting loads and make it last for long enough. We've set up this center, so remote applications in challenging environments. That basically means robotics anywhere you don't want to send people. You certainly don't want to send people inside a fusion device, because it has lots of irradiated material and tritium embedded in the walls. Neither of those things are good for you, so you want robots to do that. And we need lots of actually dissimilar robots. So from quadrupeds that go around with sensors and do easy manipulations, to drones for sensors, to very large boom robots for picking up high payload things, which might be hundreds of kilos or even tons. And then you have to worry about the deflections on the joints of those booms. That they typically need to be a boom to go around a toroidal geometry. They also need to be very dexterous, so things that can pick up very large payloads at one end, but also do things on a sub-centimeter, maybe even sub-millimeter scale, to be able to manipulate and take out components, get them out, get the machine back operational again. So lots of different types of robots, and you want, ideally, just one control system which operates all of those robots and one set of control room operators. So we work on all of these different types of very dissimilar robots, and we also work on the control systems that underpin them all. Okay, so those are the technical challenges, in my view, the big things that we've got to overcome. But what happens when we've done that? So we might overcome those technical challenges. How do we actually make fusion a commercial realization? I'm going to pick up a few things here. I'm going to talk about regulation and how we bring fusion to market. I'm going to talk about money, where the money comes from. I'm going to talk a little bit about designs and work that is being progressed in the private sector. I'm going to talk about siting and where we put devices like this, and I'll talk a little bit about supply chain and development of an industry which can support this. I'll start with regulation. ITER, that big machine that I showed you before, that big international consortium, it's being built in France, and it's being treated like a fission power plant. So it's being treated under fission codes and standards, regulated by a fission regulator, and that is for sure driving extra price, billions, into the machine and increasing time. It is not a fission power plant. It does not have the same radiological risks as a fission reaction. Fission, fundamentally, when you put fuel rods into a fission device, have enough fuel for years, and if you do have a big off-normal thing, a big off-normal event, it takes a while to get the fuel out. So you can have a risk of a chain reaction. That's, what's happened when you've seen big nuclear accidents in the past. That is physically impossible in fusion. There's just not enough fuel inside the device. It will burn for 10, 15 seconds and then stop. So if you want it to stop, God knows, we all spend our careers trying to keep it going. If you want it to stop, it's very easy to stop it. So it is fundamentally a different radiological hazard. Not to say there is not a significant radiological hazard, because there is. It's just a different one. So you don't need to regulate it in the same way that you regulate fission. And the UK government are actually very progressive on this. They were the first country to bring forward a consultation on how fusion should be regulated. And they are now, right now, taking through primary legislation to enact a bespoke and proportionate regulatory regime. As I say, first country in the world to do that. And it is proposed by the government that fusion will be regulated by the Environment Agency, not the Office for Nuclear Regulation. The Environment Agency handled radiological sources in hospitals, ionising radiation. They know what they're doing, they just don't do fission, like the Office for Nuclear Regulation do. So I think that's really important, and it is already stimulating companies to move some of their output to the UK to benefit from that proportionate and pro-innovation regulatory framework. Talking about companies, we also need money, right? So you need investment in this. I talked before about 4% of global GDP to address climate change. Well, we're a long, long way off that. But it is clear that the market has growing appetite for investment in fusion. This was a survey done last year, which shows companies being born in fusion around the world and investment globally. That investment globally now stands roughly about $5 billion. Interestingly, more or less half of that's happened in the last 12 months. So there is a big uptick in the appetite within the investment market. Also interestingly, of that plethora of companies, a significant number were born in the UK, disproportionate for the size of the UK economy. And then, perhaps even more interestingly, we're seeing companies move to the UK. So Kyoto is a Japanese company, Commonwealth and TAE are American companies, General Fusion is a Canadian company. They have all moved, in some cases, quite big bits of their operation, in some cases, small parts of their operation, but have all moved some footprint to the UK. And that is to benefit from the capabilities that I've described already and to benefit from a coherent strategy in government and a regulatory framework. So it's really exciting. We're seeing genuine inward investment into the country as a result of our capability in this space. Then you need a design, right? So I'm going to talk about a few different approaches to designs here. I'll first of all talk about what's going on in just two examples of magnetic fusion in the private sector. So Commonwealth Fusion Systems, I showed you earlier, their large bore high field magnet, 21 Tesla, high temperature superconducting magnet. They are now building on the back of that a device called Spark. They've raised best part of $2 billion to build this device. They're aiming to produce a fusion gain, so produce more power out than they put in. The machine won't run for very long. It's only going to run for 10-second pulses, but it's aiming to be a proof of principle that they can get a thermal gain, more power out. And you can see the plant, and it's well progressed in Massachusetts, and so it's coming along. They're aiming to be operational in 2025, so only 3 years from now. Whether they meet those aims, I don't know, but it's an aggressive timeline that they're driving. Here in the UK, we have a company called Tokamak Energy who are trying to drive down the scale, adopt a much more compact fusion device. They, earlier this year, showed that they could reach 100 million degree temperature in this compact device. So it's a big step forward for exploring the premise of a compact, so-called spherical tokamak. Other approaches, alternative approaches, a couple to point out. General Fusion, a Canadian company, they will be building their next device. On the right-hand side is a mock-up of what they think that might look like here in the UK, so 6 miles down the road, actually, at our Culham campus. They're adopting a sort of high-force symmetric collapse of a vortex of molten lead, so liquid metal, to compress plasma at its heart and then produce fusion by going to very high densities, lower confinement times. It doesn't last as long, but they compress it to very high densities, which produces fusion. So this is sort of car piston approach. Keep pressing it down and compressing it and making fusion happen. And then another one of these sort of compression approaches is First Light Fusion. They're the first company to demonstrate that you can produce fusion using projectile compression. So not that an alternative approach you might have heard of, in fact I'll show you now, is inertial confinement, which is again going to very, very high densities, impinging very powerful lasers onto a small target, takes them to extremely high densities, which produces fusion. First Light are doing that not using very large lasers, but by firing a projectile instead. In the inertial confinement space, there's also huge progress. So this is the National Ignition Facility at Livermore Labs in the US, where they take a tiny little target, which is about the size of your fingernail. They compress 190 of the world's strongest lasers onto that target, take it to extremely high densities, and produce fusion. And in the right-hand side, you see the fusion yield over the last decade or so, incremental progress until this year, where they really had a huge gain in optimizing the geometry of that target so that when the lasers impinge upon it, they get maximum fusion benefit. So there's a whole load of different approaches to fusion going on all around the world. And in my view, you should support all of that. You know, it's such a big prize. And it's frankly, climate change is such a big challenge that we should try everything that we can to solve that, and we should get the best and brightest people working on this because it's such a huge challenge. But what are we doing? What do UKAA do? So a few words on what we're up to. For a number of years, we are part of ITER. We absolutely believe in the conventional tokamak approach, but the conventional tokamak approach does for sure lead to a big machine, big in scale, big in price. And then your penetration into the energy market is actually determined by economics, not by technology. Fission plants work, right? We know how to build fission plants, but we don't build very many of them because they cost so much. Because you have to raise 20 billion plus every time you want to build a unit, and there are very few companies in the world that can take that on their balance sheet, and you're like recapitalizing the entire company to build one unit. So that's really tough to raise that sort of money. So we're trying to drive down the scale. Now, what drives that cost? If you look at the total cost of ITER, which I said before was upwards of 20 billion, the total cost of that, roughly a third of it is going into the buildings. So big nuclear concrete buildings. And roughly a third of it is going into the magnets and the cryogenics used to cool those magnets. So if you can strip out price from magnets and put them in a smaller building, i.e. use a smaller geometry in the first place, you can strip out billions of cost. That is the whole genesis of the spherical tokamak. It's an idea we came back with in the 90s. We built the first spherical tokamak. We demonstrated that it is a much more efficient way to use the magnets. And it's, like I said, it's the magnets that you pay for. And so you can put them in a smaller volume, in a smaller building, and drive down cost. But you need a way of extracting the heat, of exhausting the heat. That's why the result that I showed you earlier about finding this novel way of extracting heat is so important, because it opens up a pathway to a compact machine. So we have embarked on a program to build a prototype, power plant, a machine that we call STEP, a spherical tokamak, compact machine, for energy production, actually produce net electricity. That net electricity will not be commercially viable, that much I know. I don't know how much it'll cost, but I know it won't be commercially viable. First of a kind never is in energy. It won't be available enough of the time, probably the components of the plant won't last for 40 years that you want them to amortize that costs over the lifetime of the plant. So none of those things are going to work, but it is a prototype. But we're aiming that it will produce net electricity. Perhaps most importantly, if you remember all of that unholy alliance of countries that are involved in ITER, most of them they're all pursuing power plant programs in parallel to building ITER, and the vast majority of them look like ITER. So they look like very big plants, 20 billion plus in ticket price. We're aiming for a plant which is a lower capital cost than those alternatives, than the big designs. The government are putting their money where their mouth is on this. They've invested now about £300 million into concept design work, and that concept design is meant to be done in a couple of years' time. So actually in big handfuls, this is roughly what the schedule might look like. So we're aiming for a concept design by 2024. Then we go into detailed engineering design, which for sure means big mobilization of partners who have got capacity, who build power plants. That might take 8 years, 10 years, and then we start construction in the early 30s, aiming to complete the plant by around 2040. That plant will be roughly the scale of JET. So if you remember, I showed you the person in coveralls before, walking around a plant. It's roughly that sort of size, much stronger magnets in a very different geometry, but roughly that sort of scale. And as a sign, not just the regulation, not just the investment, the government have also found a site for this plant. They announced it last week, that this prototype power plant will be built here. This is the West Burton coal-fired power station in North Nottinghamshire. So this bit at the top is a coal power station. This is the coal yard, where all the coal comes in. And then this half of site is coal ash. There's about 5 million tons of spent ash, which shows you how energy-intensive coal is. This is a combined gas plant here, so that will stay there. It's relatively new and will carry on operating. All of the coal infrastructure will cease operation in spring. So they're operating over this winter, not least because it's, you will have read the news. We don't have a lot of supply in this country. So they're operating for one more winter, and then they will demolish the plant, aiming to raise all of the power plant by 2028. And we will start building on this end of site. So we'll start building at this end of site. We think we need roughly about a third of that site to build STEP. And then there's adjacent benefits to other technologies could co-locate and make use of the things that you need to build power plants. So you need a water abstraction, you need direct connection to the 400 kilovolt national grid, You need a train for bringing in components, bringing in people, access to site. You probably need access to a port, and the River Trent goes out to ports in Humberside to bring in large components, indivisible loads that are not easy to bring on our motorway network. This site has all of those things, and because it's so big, it can support multiple projects happening on the same site. And then the last thing that you need is a supply chain. So you need a supply chain which is capable of building components, and a big part of ITER is exactly that, is establishing companies, new companies in many cases, new facilities, new factories, to build components of scale of power plants. And the UK has benefited enormously from that. So far, nearly 2/3 of a billion, 650 million, has gone into UK companies to be involved in the ITER project. And not just value, but also really important contracts. So the architect engineer is a UK company. The construction management agent is a big consortium led by a UK company. Most of the robotics contracts are delivered by UK companies. So there's huge value in the development of capacity in our supply chain from the ITER project, as well as the science. But to have that sort of healthy and supported supply chain, you also need benefit in the near term, right? So you need companies to want to invest in fusion and develop their own capabilities, but they need to see some near-term returns. They can't wait 20 years until they get a return. So it's really important that we show adjacent benefits. I could have shown you hundreds of examples of spillovers from fusion into lots of different sectors. I've chosen to use Luffy because they're a recent spin-out from UKAA. They came out last year. This is an AI company for robotics and industrial control. They're using adaptive neural nets to expand the operating environment of lots of different disparate types of equipment. So it's not just robots or systems which are used for fusion, but lots of other adjacent systems, and developing control software which is more resilient and robust when deployed in particularly aggressive environments. So that's one example of a spillover, but there are loads and loads of spillovers that come out of fusion and go into adjacent sectors, and that's one of the reasons that we're seeing investment into supply chain companies. Okay, so hopefully I've given you a sort of whistle-stop tour of the status of fusion, what's going on in the world, what's going on in the UK. I would say it's an incredibly exciting time for our field. The government actually has a fusion strategy. It's bringing forward legislation. It's found a site for a power plant programme, and it's investing significant money into a power plant design programme. Not just that, but we're also delivering technical results. So we broke a world record for fusion energy produced in jet last year. In the US, they broke a world record for inertial fusion energy produced. There's a new record for the strongest large bore magnet ever produced in the US. The results that I showed you on heat extraction are transformative, and many, many new facilities coming online. You're seeing power plant design programs in all of the public sector, government-funded work, but also lots of private companies now, a growing market appetite for investment in fusion. And we are already seeing big public-private collaborations. For instance, that 5 billion invested in fusion companies, there's now 6 oil and gas companies, 6 oil and gas majors who have invested in fusion companies. And that's a pretty big sign to me that the energy industry is now paying attention to fusion and sees this as a thing that they should invest in and pay attention to. So the ground is fertile, the need is clearly imperative. We as a sector have to deliver and get on with it. Thank you very much for your attention. I'd be happy to take questions.
Ian, do you want to take a seat?
Well, thank you, Ian. That's a tour de force, and probably for some people a lot to get your mind around.
Yep.
Some people in the room I know an awful lot about certain aspects of this, and some of you know quite a lot of this story anyway because you're involved with the Atomic Energy Authority and some of its partners. I'm just going to try and moderate questions or comments in the first instance. I have a few up my sleeve for Ian, but we've worked together for over 4 years on this, so I'm not going to start off. Who would like to go first? Yes, first of all here, thank you.
Excuse me, sir.
Sorry, just one rule, please. We are having people streaming in, so if I ask you to use a microphone, it's partly so that they can hear the question as well. Thank you.
Ed Gamble, leader of the Climate Party. Thank you so much for what you've just said. 2 things. One is looking into a crystal ball. If money was limitless, so you got whatever you needed in terms of cash, how quickly could we make it successful? And then a technical small point which shows how little I understand. Do you need vast amounts of water to cool stuff and that sort of thing? If you do, thinking ahead 10 or 20 years, let's just say we had a week where we had 45 degrees continuously for the week and 40 degrees over 3 weeks, would it still be able to operate? Would it need to be shut down due to cooling issues?
Yes, I'll do the technical one first and then the one that I won't answer. Look, we need water like pretty much all thermal plants. The coal station there at the moment is spec'd for 2 gigawatts thermal. And so there's an abstraction license to pull water out the river to cool that sort of level of heat will be about that need. We're not any worse than all of the other baseload plants, gas plants, coal plants, oil plants, nuclear plants that require cooling. Fusion is more or less the same, right? So it needs water on the same sort of level. I think it's really important actually that government, one of the reasons that the government I think may have chosen the river site is because of where I started the talk. And the fact that this needs to be exportable everywhere and needs to work in all jurisdictions. If you say it needs to be by the sea, just so that you've got access to a huge reservoir of water, then it only works in countries with coastlines. And that means it's not equitable and doesn't go everywhere. So I think it is important that it can work like other baseload plants do work off lakes or off rivers. So no, we're not worse than any other, frankly. So if water becomes so scarce that we can't operate, it also means gas plants can't operate and coal plants can't operate. The one thing where there's a slight fly in that ointment is putting water, because the whole point of the water is that it cools and it gets hot and then you put it back into the river or the lake or whatever, and it typically goes in a few more degrees hotter. If the whole global temperature goes up and the water temperature, baseline water temperature goes up, and you're then putting in hotter water back into that can have big problems for the whole ecology of the river system and the lake system. So. But it's not bespoke to fusion, right? That problem exists to all power plants. On the question of timelines, so I will always cite Lev Artsimovich, who's one of the forefathers of fusion, who was asked exactly the question, when will we have fusion, in a press conference in the 70s. And he said, we will have fusion when humanity needs fusion. And I think that is still true today. If there is global imperative, and people accept that there is imperative, things happen much, much quicker, right? Brilliant people, probably people in this room that know about vaccines. Typically a new vaccine's like 10 years. Gestation, licensing, rollout to at least a decade. And we did it in a bit over a year because there was global imperative. If we were on a sort of war footing, dealing with climate change in the same way, things could be done quicker because you take more risk, you parallelize up. If money's no object, you can go faster. So it's an impossible question to answer. How much faster can you go? You tell me how much money and how much risk you're prepared to take.
It is. Just to try and calibrate this, you've heard this talk at a certain moment in history. I mean, 4 or 5 years ago, none of those records had been broken. There was far less money and far fewer companies in the private sector. Governments weren't investing anything like the amount they're investing now. And when I came in to chair this organisation, things had been ticking through in a pretty regular way, working on bits of what Ian's talked about for the last 20 years, incrementally. And you pinch yourself, we've got an inflection point.
Yeah.
And now there's a lot of interest. And what's very difficult to calibrate is how you extrapolate from that. Yeah. If an Elon Musk walked into the room and said, well, we'll do for fusion what we've done for SpaceX or electric vehicles, yeah, we might be suddenly accelerated into a completely different place. I think, Ian, you and I need to have an organisation that's ready for that moment because things are speeding up around us. And we still want to be the first in the world to put a machine on the grid, by the way, in this country.
One more corollary I'll say is that it is big infrastructure, right? I mean, if you said, I don't know, go and build an airport, it will take you a few years to build an airport. There are thousands of them around the world, just because that's what it is. If you said to EDF tomorrow, here's all the money that you need for Sizewell C, it'll take them 10 years to build that plan, just because it's big, complex infrastructure that's highly regulated. Now, we shouldn't be regulated quite so tightly and on the same basis, but it will still take multiple years to build a plant, and let's be honest, it's of order 10 years, because it's complex, really complex, difficult engineering.
Okay, let's have some more questions. I've got one here, then Chaz, and then over here.
Mark Eccles-Williams, I'm an independent corporate advisor. the fact that deuterium comes from seawater is a great message for the world, because there's a lot of that. Is it correct that although tritium comes from lithium, it can also be created via the process of fusion?
Yes, if you fuse deuterium and deuterium together, then you can produce tritium as well. So there are other ways of producing tritium, but only on small quantities. Far and away the best way to do it is neutrons passing through lithium-6, which will produce the most tritium. And indeed, that's probably the only way that one could imagine being self-sufficient in tritium production. I should have said, and I didn't really say, but the quantities of fuel that we're talking about here are really tiny. To try to contextualize, I say that for the rest of my life, for another 60 years, all the fuel I need, being optimistic, all the fuel I need, you would get from one bathtub of water and the lithium that you might have in 2 laptop batteries. And so I own 2 laptops, I could go home and draw a bath. So that's it, for the rest of my life. That's the raw materials I need for fusion. So it's incredibly energy dense. You need very little of those things. Yeah.
Thank you. It's the most energy dense thing we know, fusion. Chaz.
Yeah, thank you, Ian. You're clearly a great ambassador for this. And you illustrated how you got industry involved and government involved and regulators, and you've got space and you're working with other countries. So my question is from the university perspective. One, do you anticipate a skill gap?
Mm-hmm.
And two,
we have one already.
Something that David touched on, the importance of philanthropy or wealthy individuals, etc. And again, I'm just thinking back to the pandemic. If we think of all the vaccines that were produced, and you think of all the sort of recovery trial and new therapeutics, etc. I mean, if we added up how much we spent across the planet, it's easily in excess of 100 billion.
Oh, yeah.
And so when you say 5 billion, it just seems like a bit of a drop. And so clearly we're not on a war footing when it comes to this agenda.
Correct.
But
yeah.
skill gap and pulling in wealthy individuals.
Yeah, skill gap is already here. So we're already in a skill gap. And we are, so the question before was, all the money you want. Well, if I don't have the people, then it doesn't really matter, right? I can't deliver. And I'd say that we are now people limited more than we are finance limited as an industry. Getting hold of skilled people fishing in a very small pool. So the universities have a huge part to play in that, by the way, in developing that pipeline of people. And we put a lot of effort into that, but it's not enough. We need to be doing a whole lot more to train top-class people. And then on philanthropy and the impact that could have, I showed you that picture of companies being born. To be honest, for the first 10, 15 years of that period, most of the money was philanthropy money. It was people that wanted to make a difference and change the world, but it was all at small scale. So people were putting 10 million here, 20 million there. For sure, you're seeing the market have more appetite, and I think that will be a mixture of philanthropy, venture capitalists, and sovereign wealth funds, oil and gas companies, a mixture of all of the above. And they all have a role to play in a healthy ecosystem, for sure.
Thank you, Chaz. Yes.
Hi, Ian. Nick from First Light Fusion. I had a question about the objectives of STEP. So it'll produce electricity. Will it close the tritium fuel cycle? Will it actually have a breeding ratio greater than 1? Is that one of the technical objectives?
Yep, has to, frankly, to be of any use. I think that's true of all demonstration power plants. They've got to be able to breed more fuel than they consume. So yes.
Thank you, Nick. And for those of you who don't know, Nick is an Oxonian who's spun out First Light Fusion from Oxford. And, we could spend the rest of the evening talking about associations between the labs here in Oxford and what goes on just down the road at Culham and in your facility. And it's great to have you here. I'm going to take one question through Charles from the people who are watching in.
This is a question from Keith Beard. What lessons can we learn from the UK's early lead in commercial fission power, Calder Hall, etc., to avoid a loss of capability and leadership with fusion?
It's a great question. So sort of first commercial reactor, first advanced reactor, and now we buy power from a French company largely. And maybe in the future a US or a Chinese company, but we have pretty much no indigenous capability today. So yeah, I think that's a salutary lesson. by the way, nuclear is not the only example where the UK has had a lead in R&D and innovation and then squandered that lead. So, given the government's agenda is growth, 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 I think there's huge opportunity for realising economic benefit from this technology and its adjacent technologies. So that's absolutely our aspiration, capitalise as much of that value in the UK, bring prosperity to UK companies on the back of a position of leadership in R&D.
Thank you. Patrick.
Yeah, Patrick Grant, Oxford University. Your point about the sort of the quantum of the fission plant being too expensive, 20 billion, something like that, and how the STEP idea hopes to reduce the unit cost. But fission is also learning that lesson with the development of small modular reactors.
Yeah.
And also getting government support. I'm sure that you would say we need both, but the reality probably is that there may be a sense that there's a competition for scamped funds, and how much can you work with the SMR idea alongside STEP, or how much do they have to go on different pathways?
Yeah, so two comments on that. So one, SMRs in fission and spherical tokamaks in fusion have a fundamental difference in that you can get the same thermal output from a compact fusion machine as you can from a large fusion machine. In fission, pretty much power goes with size. Right? You make it bigger, it produces more power. Right? Hinkley Point will be 3.5 gigawatts. Rolls-Royce's SMRs are 440 megawatts. They're smaller, but they produce lower power, and you need more units to get the same amount of power. So that's just how you raise. I mean, you're more or less raising the same amount of money, just in a different way. In fusion, that's not the same. The geometry, you could still produce the same thermal power in a different, smaller geometry, is the aspiration. So it's a genuine economic benefit rather than how are you raising the money. In terms of, obviously you've predicted my answer to the question about should we be doing both and how can we invest in both? I mean, I think the size of the problem is so large, we should be throwing absolutely everything at it, all technologies and as much of as possible. It's a huge frustration of mine that the energy industry at large spends so much of its time fighting about who has the best technology when we should all be saying we should invest in all technologies, not arguing about whether it's offshore wind or carbon capture. I mean, just all of it, please, and as much of it as possible. And the energy industry falls into the trap of saying in front of government, my technology is better than your technology. It's so stupid. We should all be supporting one another's technologies and all be saying, government, you need to invest in all of these. So I'm not going to bite.
And I think, just to put this in context, someone will correct me if I've got this wrong, but in general orders of magnitude, the oil and gas sector is expending something like $500 billion a year on R&D for more extraction. Yeah. And, we're talking about a few $100 million for the design of one of these power plants. So we've really got some work to do to bring money in this sort of direction. Please.
Hi, I'm Vinay Ranning. I'm a political leadership scholar here at the university. I have two quick questions. I'm a complete layman to what you just presented. It was absolutely fantastic. And along the same lines, how do you aim to kind of communicate this to the public, to bring them along the journey? Because I feel like misinformation could ruin this project. And secondly, just on that point, how much, relative to other forms of renewable energy, how much power are we kind of talking from fusion relative to wind, solar, etc.?
Yeah, okay. So I'll do the second one first and then come back. In fact, I might let Tim talk about comms. So the second one first. So we're imagining, roughly, that fusion will be sort of gigawatt scale. So it's a replacement for gas and coal and things like that. The penetration into the market, which really determines how much of the market you make up. How quickly can you roll out? How quickly can you build plants? Now, looking at the past is not necessarily a good guide to the future. But if you look at when the advent of gas and it started taking market share from coal and oil, it was going at a growth rate roughly of 30% a year. So it was every year, 30% more plants. The same was true of fission. So after the first fission plants, then the growth rate of fission up to 3 Mile Island was about 30% a year. So if you work on that basis, that big infrastructure plants, which fusion will be, the growth rate is something like 30% a year. It takes you about 30 years to get to 10% of global demand. So it's not a solution for tomorrow, but by the way, nothing is a solution for tomorrow because it all takes time to build. So as I said right at the start, you know, global net zero is some kind of fantasy. It's not going to happen. And we should be doing far more today to get closer to it, but we won't get there. So this notion that it's just all going to be all right, it's not all going to be all right, right? We have to take much more severe action. And that's the sort of growth rate. So I think you could get to maybe 10% of global demand over a 30-year period, something like that. On comms, yeah, I totally agree that we need to be much more visible. It's quite hard for us as a government organisation to spearhead that. The government, the Energy Department, have started doing a public opinions tracker on energy at large. They started including fusion in the questions that they do. They do like public surveys, public opinion surveys, about 2 years ago. When they started, I think it was 20% of people had ever heard of fusion. I think when I talk to the general, most people I say the word fusion and they either think Gillette razor or they think some sort of combination of cuisine or something like that, right? So, and they're not, beyond the 20%, there were about 10% who just thought it was fission and conflated it, and 60% who just never heard of it and no idea what it meant. That's improving, so both numbers are about doubled now. So I think it's like 60% think they know about it, and 20% of them are actually thinking of fission rather than fusion. So it's improving, but there's a huge amount to do to increase public consciousness. And with public consciousness, by the way, comes more imperative and more money. So it's very much in our interests to make more people aware of it. It's a tough thing to do. If you've got good ideas of how to do that, I'm all ears.
Thank you, Ian. The lady here, I think, was nodding because you were going to ask and make a similar comment, but it's been answered now. So let's go across to Leo.
Yeah, this is Leo, new energy investor. So it's very, very impressed with all those achievements you lead. Two questions. The first is for all those new technology you said we all should embrace. So, for example, how do you view, or would the UKAEA take the approach of the high temperature superconductor to achieve high Tesla proven by CFS? How do you view, like, how would you combine with your current model, or if you, just how do you view this? From our observation, it's quite a big step forward. And second is, how do you view the international collaboration in terms of commercialization of fusion? Because, for example, Bill Gates put quite a long time effort in fission in China, but he had to stop from U.S. government's regulation or certain political opinion. But for fusion, do you think it would be better because this new ITER very big collaboration program, or how do you see it in terms of a commercialization effort? Thank you.
Yeah, okay, so on high temperature superconductors, yes, I think everybody in fusion will use high temperature superconductors and benefit from magnetic fusion, will benefit from a higher magnetic field if we can overcome some other challenges that brings. Right, so that the higher field means higher confinement, which generally means that the exhaust problem is harder. It also means huge structural forces between the magnets. So how you engineer that and actually build a machine that doesn't blow itself apart is a big challenge. Now, it doesn't mean it's an insurmountable one, and I think probably we'll end up in a sweet spot, which is not going to the very highest magnetic field, because at that point the engineering challenges are too large, but you'll still benefit from HTS in going up in field a bit compared to where we are with low temperature superconductors. So that's my personal opinion. I mean, it's navel gazing, right, to know exactly how far you'll go and how much benefit you'll get. But the clue is in the name, magnetic fusion, right? So magnetic field is a really good thing. So if you can go to higher magnetic field, for sure we all benefit. So absolutely we will want to use high temperature superconductors. On the international collaboration aspect, I said to Patrick, you should throw as much money at all things. I have sort of the same approach on collaboration. I think that there's a place, absolutely a place for proprietary information and companies doing their own thing in a protected way. I also think that companies should collaborate with companies and companies should collaborate with public labs because we all get there faster. And on the public side, I think governments should work with governments and we should all get there faster. It's a bit like vaccines, right? I mean, you just all got to work together and all pull in the same direction and try and get there as quickly as possible because the imperative is so large. So,
And just in the example of vaccines, we have healthy competition between different designs
Sure.
of vaccines that forces the pace. And, you know, in history, any major radical innovations have been hothoused when there have been healthy options that the private sector can go after and so on.
But
And
also collaboration at
and
the research
collaboration
level.
between them, exactly.
So
yeah.
I think that's all part of a healthy ecosystem.
We're just coming towards a close here. We'll take one question over here and then one from you, class. Yes.
Chris Grosvenor from Oxford. In IP, so you made some comments about the clunkiness of the ITER and demo projects with the multi-international partnerships, and that slows things down. But one of the things you also said was they share IP.
They do.
With the more programs that are funded by private investment, they tend to be extremely protective of their IP, and one can understand why. But that means it's not shared. And I wonder if you think that that's a problem going forward. And if I might just anecdotally, I'm trying to sign an agreement, a very small one, a studentship agreement, and the IP clause is impossible.
Right.
And that's just a sort of symptom of I think, of the fact that it's a different world from dealing with ITER.
Yeah, so on the public thing, I mean, that's the nature of ITER, right? I mean, it was never going to be, and it was one of the reasons that the project is more cumbersome than you would like, ideally. As an example, the big magnets, right? So the very large magnets. The sensible way of, you need 18 of them, the sensible way of running an engineering project, building those very large magnets, is to go to one supplier and say, build me the same magnet on the same rig to the same spec. Now, let's imagine that all of those partners had gone into the contract and, say, a Chinese vendor ended up building the magnets, and you're the US, then you want to build a power plant, you're totally beholden to that Chinese vendor to build magnets for you. So that was never going to work out that way. So instead, you've got 6 different partners providing 3 magnets each, right? So it's whilst the IP is shared, also the capability is shared. Now, long term, that's a really good thing, because you've generated competition, and you now have 6 factories and 6 companies that can do it. But for that project, it adds a whole quality control challenge, a whole legal complexity of, well, if you deliver strand later than this partner, who compensates who and how much? And so the contract just ran into legalese for many years while all of that got sorted out. So IP, as much as we would wish it just to be a thing on the side, it's not, right? It does determine timelines. On the approach of IP management by the companies, I mean, they all genuinely have different approaches to this. Some I know nothing about, and nothing's in the public domain. Others are very open with their results. They publish quite a lot of it in open literature, and some parts they keep proprietary, and some parts they will try to patent. And they recognise that, you know, that's their crown jewels, and the rest of it they're very open and liberal with. And they will all get there faster if they collaborate. So, you know, we see this in all industries, and some bits are proprietary and some bits are not. So I don't think fusion...
So that's a good segue to our last question and comment from Klaas de Boer, who's the chairman of General Fusion, which is building a machine using private sector money down the road on the campus here. So let's hear it from your side, as well as your question, if you've got a different question, Klaas.
I did have a different question for Ian. But thank you for the introduction. That saves me doing it. Ian, when you described ITER at the beginning, you talked about evidence-driven approch and the timelines that come with it.
Yep.
You then talked about STEP, which operates on a different timeline.
Yep.
Can you give some color on to what extent STEP is still evidence-driven, and to what extent you've parallelized the approach, and with more funding and more appetite for risk, could you squeeze those timelines further, or and what sort of trade-offs are in there?
Yeah. Okay, so that's a really complex question, Klaas. Let me give you one example, right? So at the moment, our technical thinking around STEP is that we will not have low activation materials on the timeline that we're talking about, with a supply chain that can manufacture them on the volumes that we need. So probably that prototype, that first of a kind, will produce more irradiated waste than we want long term. But it's a prototype, it's a demonstration, and we're roughly philosophically okay with the fact that the first of a kind might not be optimal. Now, in parallel, you continue working on a better material, a better steel, for the next of a kind, so that you can drive down your waste volumes longer term. And there are a number of things like that. We also probably won't have the lifetime of the materials. The first wall might swell, might get brittle, might crack, and we might have to replace it after a few years rather than a decade. And again, that's kind of just, it's a risk that we're accepting and saying we want to get there faster, so we're going to take some of that risk and parallelize up, building a prototype with development paths for the next of a kind that come after it. It's a fundamentally different philosophy to the European demo, which is saying, first of all, we need a material, and then we need to qualify it and test it, and then once we've done that, we'll build a plant using that qualified material. So they're different philosophies, and they drive different timelines. Did that answer your question?
I think that's a discussion over dinner or drink, actually, Klaus. Look, let me try and just, I'm not going to summarise anything other than try and wrap up this wonderful presentation from Ian and good questions and contributions from you. You know, we're at the best university in the world because the Times Higher Education Supplement says we are for the 7th year in a row this week. Look, I just want to give a shout out for science, engineering, manufacturing, technology, spin-out, public-private working together. And what Ian's shown, actually, if you just absorb, those of you who don't know it so well, some of those facilities that have been constructed in the last 5 or 6 years, some that are just being built at the moment, in this country, are a beacon. They don't exist anywhere else. And actually, one of the reasons I think some of these wonderful private sector companies want to come and buddy up here is because science is still necessary. We've still got to prove that these materials are going to hang on in there under these extreme forces. And you know, the history of any radical major innovations that are long-lasting is a history partly built on the construction of new scientific instruments and capabilities. And one wonderful thing that we can see here in this country is that foundation for fusion. We have the best facilities. I don't think anyone would argue about that. We might not have the best facilities in 5 or 6 years' time if we don't keep investing and building the talent to use them, because other countries are doing this stuff, and quite rightly, and we need everything. But I think it is a wonderful combination. There are at least 34, 35 universities working with Culham. Oxford's in a privileged position for 2 or 3 reasons. One, it's its neighbour. And 2, we've got some great science and long tradition of history of working on plasma physics and other areas. But I think that combination, Ian, and we need that combination of the private sector in there, and a huge amount of spillover. Maybe it's for another talk, Charles, but you know, what can happen with that capability in magnets? What can we do with those robots? What can we do with the new materials that we're starting to create in other industries? It's just a fabulous horizon for us to look at. And I think on that note, we've got a fabulous leader of all of this in Ian, who spent his time with us this evening, rather than managing what is a very complex institution now, the Atomic Energy Authority. Thank you, Ian.
You are very welcome.